Okay. Let's continue on today's lecture. So, I was talking about the loop carrier dependencies in the loop honoring. So, as you can see, you can find the dependency on the memory of this code. So that dependency is caused by this code. Okay, where's this code? So when you see this code, the load instruction is load the AI actually. It's a AI, and then the AI plus 2 is stored in the by the instruction O4. So here, so because of this dependency, there is a loop carrier dependency, and then I already talked that. Uh, I already told that because of this loop carrier dependency, the 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 number of loop unrolling is also limited. So this is the loop carrier dependency, and then this diagram is the data dependency diagrams. So if you see this figure, then you can find this instructions here. So each node represents the single instruction. So, and then between those single instruction, there is a edge, and also it's called the arc. And then in the arc, there is some values like this deep, and then this arc is labeled with the deep and minimum. So deep is the number of iterations between the two operations, actually two instructions, two operations in the VLIW. So, and then mean means the minimum number of clocks between the two operations. And so that is the latency between operations. So if you see this diagram, then you can, and then it's in the previous code, then between this load and add instruction, there is the dependency here, data dependency is here, and then based on the some latency information we mentioned before, the difference is 2. And then what about the iteration? So iteration is 0 because that is the operation in the same iteration. So this is the operation using AI. Okay. Now, in the same way, we can define some arc, and then the minimum and difference number, like here and here. So as you can see, this minimum latency defines the distance between instructions in the same iteration. And then actually for auth, from the auth, the O4 and then O5 receives the so O4 receives the value from the O3. The O3 receives the result from this add instruction here, and then also O4 receives the data from this add instruction O2. So actually we can we can draw the dependency graph, such as the O2 is also connected to O4, though the O2 is connected to O4 with the difference number is 0 and then minimum number is 3. So it's the same. So that means that for the O3 and O4 is located at the same clock cycle slot after the O2 because this minimum distance is the 3. And how about this O1 and O4? So as you can see, this is the O4. Yeah, O4. Yeah, right. There is O5 is here. So for the O4 is O4 stores the result to the AI plus 2. So the minimum distance is 1, but what is this, the iteration distance is 2, because with this by the instruction O4, the I plus 2 is updated. So this is the, so this, and then this value is required by requested by the load instruction O1 and the second iteration. So based on this data dependence diagram graph, data dependency graph, then we can build the kernel of the software pipelining for this case. And then, okay, let's see this software pipelining table. So based on this data dependency graph, then we can arrange the instructions in the iteration 1 slot, iteration 1 column. So it's O2 is here, O4, O1 is here, O2, and then O3 and O4 can be located at the same clock slot, and then O5 is here. So this is the same to the previous example, previous software pipelining example. For the iteration number 2, but it's a deep. So the problem is that, so this example has the loop carried dependency. The problem is that the O1 of the iteration number 3 should be located after O4, right? Because the O1 reads the data stored by this O4. So this relation should be kept in the software pipeline. So O1 is located just after the O4 here, and then considering this relation, so the second iteration of the O1 is located here, not here. So normally if there is no loop carried dependency, then O1 can be located here, but in this example, due to this loop carried dependency, the iteration O1 of the iteration 3 should be located here. So, and then for some regularity, O1 of the iteration 2 is located here. So based on this result, the kernel of this code, software pipeline code, is this here. And then based on this kernel, the kernel of the software pipeline is determined like this. So what's the problem? Even though we use the software pipelining technology, there are many ups. There are many empty slots. So actually, if we see this table, empty slot is here, 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 and then kernel also, the kernel occupied 3 clock slots here. So this is so inefficient. So actually for this veritable processor, the peak IPC is 5, right? But in reality, this one more nope is here. So actual IPC for this code is 1, 2, 3, 4, 5, 6, 7, 8. Maybe 8 divided by 3. It's about 2 and 2.67. So so with this software pipelining kernel, this kernel cannot fill the all OP slots due to the loop carried dependency. And then with due to this loop carried dependency, actually the first instruction of this iteration number 3 should be located here, and so that is some performance bottleneck of the loop unrolling. Okay. Yeah, so with the for this loop unrolling, then we can apply the rotating resistors to avoid wall hazard. Okay, so these loop rotating resistors are allocated to the resistors that has the data dependencies. Okay, and then let's see the non-cyclic scheduling, and then as a trace scheduling. So actually, so it's the some cumbersome. It looks like cumbersome because the speculation is handled by the compiler techniques and the software, and then that sounds weird. But the speculation technique can be also applied by the compiler. Also, this speculation technique is used to increase the performance of the code. It's a kind of some technique, compiler technique to increase the performance, but uh, so it's a it's a software speculation technique. It looks weird. 네, 어쨌든 하드웨어가 지원을 하지 않기 때문에 소프트웨어로 이제 컴파일러로 스페큘레이션을 지원하는 거고요. 어쨌든 이 스페큘레이션을 지원을 하는 이유는 아주 베이직 블락이 너무 작아요. So the basic block of the code is too small, so the effective optimization technique cannot be applied if the basic block size is too small. And then we frequently use the if else statement, if then else statement. And then this if then else statement is translated into the conditional branch instruction actually. So if then and then else, and then some statement A, and then statement B is here. So based on the condition of the if then else statement, statement A can be executed or statement B can be executed. This is the flow of the some similar code. So this is the if statement, and then based on this if statement, the code basic block B can be executed or basic block D can be executed. And then we know that this if then else statement is implemented by conditional branch instruction. So based on the condition of this branch instruction, the B can be executed or D can be executed. So when the compiler analyze compiler analyze the code, then compiler can draw this some flow graph from the basic code, basic blocks. So this flow is frequently found in the normal code. So what's the problem? So if there is no speculative execution, then until this result of the branch instruction is resolved, the processor does not know which path will be executed. So processor need to wait here until the branch instruction is executed. So problem is that the Vliw needs the many instructions, many operations to increase the performance. But I'm actually in the previous class I mentioned that the basic block size for the normal program is about 4.5. So that means that only 4.5 instructions inside of the basic block. So how can compiler apply the optimization technique with the 4.5 operations actually for Vliw processor? It's ridiculous. So compiler also applies the speculative scheduling actually for this if then else data flow. So in the compiler, compiler generates some big basic block with the A, B, C. Actually, the compiler analyze the code, and then compiler selects the some most likely executed path. So in this case, the B is the value of the B is 1 for the high probability. So compiler think that A, B, C, for the most of the case, the code flows from A, B, C. So compiler think A, B, C is the big basic block, and then applies the some speculative applies the some optimization technique. But then what's the problem? Sometimes the B value is 0. So in the case, the the basic block D is executed instead of B, but compiler already applies merges this basic block A, B, C, and applies some optimization technique. So how can compiler apply this speculation? So compiler generate some compensation code for the speculative path. For example, so if this path is the some the path that could be executed, with a lower probability, then if this path is executed, then compiler cancel the result of this basic block, and then execute the D, and then resume the execution of this C. So for example, the flow looks like this. A is here, and then B is here, and then C is here. So this is the big basic block, and then compiler applies optimization for this big basic block. So this is executed, but the compiler detected the B is 0. So in that case, the compiler cancel the some compensation code for the compensation code. So first cancel the B, cancel the some executions made by B, so here, and then execute the D. So this is the compensation code for the if B is 0. So actually there is some technique for the some optimization. So actually the store is very critical. So we can move this store instruction, and then also the speculative execution of the store instruction is very dangerous. So actually this compilers cannot apply some optimization for the store instruction, but there's no storage here, and then should not affect the other trace D here. Is the speculative code motion. So and then also some specialized instruction is conditional or predicated instructions, and then this predicated instruction means that the instruction is executed if the condition of execution is true. And then so this is the some example of the predicated instruction. So this is the normal code. So Bn is here. So this branch instruction tests the content of the R1. If the content of R1 is not 0, right, not equal to 0, then jump to the L1. So what's the meaning of this code? If the condition is met, then this move operation is cancelled. And then you can easily find this similar code in the normal application. So and then we can translate these two lines of code with the predicated instruction. So this predicated instruction implement this example BNG and move instruction. So C move G. This C move G execute the move operation, but it tests the value of R1. If the value of R1 is non-zero, then this instruction performs the move operation for R2 and R3. So actually, this type of operation is found in the ISA. ARM has the CPSR register. That's the CPSR, current program status register, and then based on the status of the CPSR register, the instruction can be executed or not. So ARM also supports this predicated execution. So what is the benefit of this predicated execution? The branches can be removed. So that helps code scheduling. It's a great effect, a great advantage of the predicated execution. So if the branch can be removed, then the size of the basic block becomes larger. So then the compilers can apply optimization technique more easily. And then also control dependency. So what's the control dependency? It's a control. It's a different paths by the branch instruction, and then this control dependency can be replaced by data dependency. This is because this so actually when this operation or instruction is fetched and then this issued, then this instruction should be executed. And that means that the tested and executed. So the control dependency, sometimes the instruction is fetched or issued or not, and then this dependency is changed to the data dependency with this new type of instruction. And then these advantages. All instruction must be executed regardless of the condition. So so let us assume that this part is so large, so there are actually not moving. This part may include many instructions, like more than 5 instructions. So if the branch instruction is taken, then this instruction is not executed. So even this instruction is not fetched, not executed, and then not tested. But with the predicated instruction, these all instructions, including this part, should be fetched, issued, tested, and executed. So with the branch instruction, the number of executed instruction is reduced, but with the predicated instruction, the number of fetched instruction may be larger. And then this predicated execution instruction is only good for the short skip or if then else block. So actually I already explained about this issue. So actually this is very good for the short skip, but if the the part that is sorry, if the code fragment that can be skipped by the branch instruction is very large, then it's not good. And then if you see this instruction and this instruction performs the test and move operation, so actually based on some normal operation, this test or checking some values operation should be added. So actually predicated instructions may require the more complicated hardware engine, so then may slow down the clock frequency. Exception. So exception is the very difficult part. So, and then actually this instruction include actually two part, test and execution, right? The move operation. But the let us assume that move is the exception is exception happens and during the move operation, that the instruction need to report this exception if the condition is only true. That's right? So, for example, if the divide by zero operation, so if x, so for the divide by zero exception, we can make the some what's this? We can make safely write the code like if x is not 0, then y equal a divided by x. Okay, so this example program statement can be implemented with the predicated execution. So if the x is 0, then that is divided by 0 exception, and then with the normal instructions, then this exception will not happen because only this part is executed if the x is not 0. But if we use the predicated instruction, then so this instruction, if this instruction is executed, then divided by 0 can be detected. So tested and but detected, but this part can be executed, but it's not updated to the status of the processor. So in this case, the exception must not be reported, right? So enable them only if the condition is met. This is the so for the exception should be handled more carefully. So and then limited to two-way conditions only. Actually, these predicated instructions only can be applied to the very simple conditional branches. Okay. Then both in some architecture and then some instructions architecture, all instructions are predicated. For example, Intel IA64 Itanium processor, and then this ISR has both the instructions of this ISR is all predicated. Interesting. Also, the ARM also has the predicated instructions. So, compiler speculation with the hardware support. So, the branch is here, is a and then some other instruction is here and here. So based on this branch instruction, this instruction can be executed or not, but the compilers schedule these instructions for the speculative execution. So then that means that the branch instruction is moved after this code, and then this instruction is speculatively executed. It's just executed, but based on the result of the branch instruction, the result of this part can be updated or not. So advantage. So why this weird scheduling can be applied. So advantage creates longer schedule code. So that means that makes the code size bigger. Actually for the basic block. So this technique is applied in order to enlarge the size of the basic block. And then if the size of the basic flag is large, then compiler has the many resources to apply the optimization techniques. So with these techniques, then compilers can increase the IIP. And then, but the compilers cannot move store instruction. Actually, the store instruction cannot be executed speculatively. So for the out of the processor with the speculative execution, the store is only executed at the top of the ROV, right? So when the instruction is committed, store instruction is executed. So store instruction cannot be speculatively executed. That's true, and then that is very critical, because store instruction can change the content of the memory. So if the content of the memory is updated incorrectly, then it will generate the incorrect data or incorrect answer from the computer. And so, but the exception is the also difficult issue. So how can the compiler handle the exception? And then this exception handling should be supported by the hardware. Yeah. So, so this is the original code, and then with this original code, load instruction is here, and then branch instruction is here, and then load instruction is here. So because of this branch instruction, this load instruction cannot be executed. So compiler can move this load instruction and before the branch instruction for the speculative execution. So store instruction is moved to the before branch instruction. But the exception is exception handling is the problem, because when the load instruction is moved to here, then another source that the exception happens on this moved load instruction at this point. If the exception is detected, then the computer processor needs to report this exception to the operating system. But this load instruction is speculatively executed. So branching by the result of this branch instruction, this load instruction can be executed or not. But as the load instruction is executed always is executed or is always executed, speculatively the exception may detected even though the branch is not true. Branch is not taken. So exception happens, then the exception should be reported. So in order to avoid this case, we can add some new instruction that handles the exception. So this is some new what is that? So improved code, new idea is applied to this code. So for this load instruction, the special bit is added. So that means that this .s, the postfix represent this load instruction is executed speculatively. And then at the location of the original load instruction, the check instruction is inserted. So this check instruction is check this speculative bit, and then the status of the exception. So even though the exception happens for this load instruction, then the report of the exception and then handling of the exception is delayed until this check instruction is executed. So it is because the check instruction can be executed or not by the result of a branch instruction, right? So this branch instruction is here. Okay. So the exception happens for this load instruction, then the processor knows that this load instruction is executed speculatively, and then so the processor just stores the update the exception status register, and then if this check instruction is executed, then check instruction, and this check instruction is executed for the R15. So in this case, the processor knows that the load instruction is here, original load instruction is here, then the exception is also should be applied to the original load instruction. So in this case, and then they know that the exception handle register is already updated by this speculative load instruction. So the processor reports the exception cases and then calls the repair code. So it is because some instructions are speculatively executed. So, so repair code should be also executed. So yeah, it's so weird. So what else? So that is what is done by out-of-order processor with a speculation. But as the hardware does not support for this speculative execution, then software actually compiler need to support this rollback of the speculative execution. Yeah. And then the exception can be also approximatively detected. So this is the speculative load here, and then the load, this speculative load is with a poison bit, just a poison bit. The load speculative load just to set the poison bit for only R14 if the exception happens. So exception is detected, then non-speculative instruction. Non-speculative instruction reads the poisoned register. So actually this poisoned register is set for the R14, and then if this poisoned register is read by non-speculative instructions such as this add instruction or store instruction, right? R14. Then if the poison bit is set for this R14, then the processor knows that somewhere in the spec somewhere before the exception happens by some previous speculative execution, then processor knows that the exception happens in the before. So this poison bit is propagated by the speculative instructions, and then so just is approximately exception is handled by the processor. So somewhere before by the speculative execution, the exception happens. The processor only knows that information. So this is the approximate exception model with the poison bit. And then if the exception is handled, then poison bit is reset. And then some normal operation is resumed. And then also this speculative execution can be applied for the memory disambiguation. So actually we already mentioned covered about the memory disambiguation in the out-of-order processor with the speculative execution, and then the same mechanism can be applied by the compiler. So let's see this example. So this is the original code, and then the load instruction is located after the store instruction. So that means that before the address of the store instruction is resolved, this load instruction cannot be executed because the load instruction does not know the target address. But normally in the store instruction just stores the final value to the memory. This is a normal operation of the assembled code. So it is actually, for the normal case, it is good that if the store instruction is located in the bottom of the code. And then normally in the load also it is normally good if the load instruction is located on the top of the code, because the load instruction may take long cycles to fetch data. So this is the optimized code with the load instruction is moved to the top of the code, and then store instruction is here. So this is some ambiguously the load instruction is executed. So if and then this is some special instruction for the check instruction. So store instruction is executed here, and then this is some address for this load instruction. Okay, this load instruction. So if this address of the load instruction is checked by another store instruction. Store instruction is here. So if the check is done lately, but if the check is false, then some repair code is executed, and then the repair code, with this repair code, then the original code is executed. And so this is how this memory disambiguation is handled by the software technique, the compiler technique. Okay, so 우리가 이제 지금 이제 VLIW에 대해서 이제 좀 배웠는데요. 사실 VLIW는 약간 그 혁명적인 레볼루셔나이즈 혁명적인 그런 프로세서 구조라고 이제 볼 수가 있겠습니다. 그러니까는 하드웨어가 이제 처리를 하는 부분들을 소프트웨어적으로 컴파일러가 최대한 분석을 많이 해가지고 하드웨어는 아주 심플하게, 그 다음에 소프트웨어가 열심히 일을 해가지고 소프트웨어가 이제 컴파일러가 옵티마이제이션 테크닉을 한다든지 스페큘레이티브 엑스큐션도 수행한다든지 이런 부분들을 이제 하는 거죠. 근데 역시나 이제 거의 많은 그 부분들이 컴퓨터에서 이제 수행되는 많은 코드들이 그 스테이터스가 이제 다이나믹하게 이제 결정이 되기 때문에 그 지금 VLIW 같은 테크닉은 좀 많이 안 쓰이죠. 그래서 거의 모든 프로세서가 이제 다이나믹 아웃 오브 오더 프로세싱을 지원을 하고, 그 다음에 스페큘레이티브 엑스큐션도 다이나믹하게 처리를 하게 됩니다. 예. 그렇지만은 이런 여러 가지 그 컴파일러의 그런 테크닉들이 우리가 이제 알면은 굉장히 이제 좀 유용하게 쓸 수가 있어요. 특히나 앞에서도 얘기했듯이 그 연구를 할 때 그 올드 이제 테크닉이라고 하더라도 우리가 이제 잘 그 현대적인 연구에 다시 이제 리바이브 시켜서 적용을 해도 아주 좋습니다. 예, 사실 세상은 돌고 돈다고. 사실 머신러닝도 마찬가지죠. 머신러닝도 우리가 새로운 알고리즘을 해서 하는 게 아니라 딥러닝 같은 경우에는 오래전에 이제 이미 나왔던 이론인데 지금 컴퓨터가 지원을 잘 하다 보니까는 머신러닝이 뜨는 이런 상황이 발생한 거죠. 예. 그렇습니다. 벡터는 어떻게 할까? And then I will briefly 그래서 이제 벡터에 대해서도 이제 조금 다루고 넘어가도록 하겠습니다. So I will briefly explain about the vector processor, and then actually this is not a difficult topic because vector processor just execute the vector operation like vector add b1, b2, b3, and then b1, b2, b3 are the vectors of the scalar, and then this scalar has the same type and then same length. scalars of the same type, so it's the same like integer or long or and then long, or also this vector length is the same length. So actually, I believe it's the same. This is the vector, so it's the group of scalar values, and then this is the v1, and then v2 and v3 is here, and then this add operation is applied for the each element of the vector data. So this is the vector processor, and then so actually it is easy. And then actually the vector machines are widely used, and then it coexist with the normal processor because the recently multimedia application widely used applications are widely executed in the computer systems, and then for this multimedia applications, vector operation is frequently found. So if the computer processor supports the vector processing, then it can accelerate the operation of the multimedia applications. 그리고 벡터 오퍼레이션은 많이 발견되죠. 역시나 그 멀티미디어 오퍼레이션 같은 경우에도 많이 쓰고 있기 때문에 이런 벡터 오퍼레이션은 뭐 많이 발견되고요. And then also the special instructions are added to the x86 instruction set architecture, such as the SSE, SS123, for example, this. And then these instructions are related to the vector operations. So these vector operations are widely observed in the normal processor. Yeah, so and also recently we frequently use the GPU, is the graphics processing unit for for machine learning applications, some scientific applications, also in the game and video applications. So actually, these applications frequently use the linear algebra. And this linear algebra is used the matrix operation. And then what's the matrix operation? The matrix is also the group of vectors. So vector processing is very useful for the modern applications. So this is very useful for the scientific and machine learning applications. So also GPU, the graphics processing unit, support the vector-like operation. Actually, the GPU has the CMT architecture. It's a type a little bit different from the CMD architecture, but this GPU is also support the vector-like operation. So actually this is some execution cycle of the vector add. So actually for the vector add, the operation is a vector element, so another vector element. So actually the operation is the element by element add for the vector add. But if the vector length is the 64, and then if this element by element addition is executed, then number of adder is 64, and this is the inefficient hardware design. So normally for the vector operation, the vector hardware is implemented like this. This is the vector register, and then this is another vector register, and then this is the adder. And then at each cycle, the single element of the vector register is fetched and then executed by this add instruction. So let us assume that the add pipeline has the 10 stages, the floating point add operation, and then total execution time is, and then vector length is the 64. So the one instruction is calculated by the floating point adder, then it will take 10 cycles. But normally this hardware is implemented with the pipeline architecture. So when the add instruction is add instruction has the pipeline stages, and then if the element 0 is executed here, then element 1 can be executed in the first stage. So it's a pipeline. So this is the total execution time of this vector add, 10 plus 63, and then it's equivalent to the 9 plus 64. So 64 is the length of the vector, and then 9 is the startup time. So number of stages minus 1, and then it's it's equivalent to the length of the vector. So it's the 73. So 73 cycles are consumed. Now this is the how vector processor support the vector operation with the vector register. 뭐 그렇긴 한데요. 그 GPU 같은 경우에는 이거 우리가 이제 벡터라고 부르는 그런 뭐랄까 그 어떤 데이터의 이제 그 벡터에 대해서 그 각각의 엘리먼트마다 그 엑스큐션 유닛을 가지고 있습니다. 이제 그 심티 레인마다 이제 엑스큐션 유닛을 가지고 있다라고 얘기를 하는데 이거랑 좀 다르죠. 패러럴 프로세싱이 좀 더 아주 어그레시브하게 이제 발생하는 거죠. So advantage, so the simple vector operation is supported by the hardware. Also, actually, for the vector operation, each operation needs some bulk operation, like so same operation can be executed for the 64 element, and then if this scalar processor, if the same operation is applied for the 64 element, then we need to use the iterative loop, right? So for example, for the 64 for the vector operation for the that has the 64 element, then we can use the for I equals 0 and I is less than 64, and then I plus plus, and then some operation is here. So the 64 operation is iteratively executed. So this is the normal operation by the scalar processor, but for the vector processor we can only use the vector load, blah blah A, vector load B, and then vector add C A plus B. So this bulk operation can be easily executed by the vector operation. So and then another good thing is that we can reduce the size of the instructions. And then for the independent and vector element, and then we assume that there is no data forwarding, and there are no data hazard, and then no control hazard. So simple operation can be just applied. And then disadvantage. So also for this type of code, this type of code should be translated into the vector operation with the compiler, by the compiler. So the vector processor just relies on the sophisticated compiler, which can translate this code into the vector operation. But so recently we used CUDA for the GPU programming, and then this is also such a kind of a compiler. But for the CUDA, the user, programmer, need to translate this iterative loop into some single thread instructions. But yeah, actually this operation is also can be done by programmers, and then normal programmers, and then that is only applicable to the class of application for such domain of the application, such as the multimedia or some scientific applications. And then normally this is very important for modern computer architecture research, because nowadays we are living in the many computer architects mention that today's era is the domain. Today, in the currently domain specific architecture is very important. So what is the domain specific architecture? This domain specific architecture can or accelerate the performance of the specific domain application, specific class of application. So this is a disadvantage of the what's that? The processor, but it's not a disadvantage nowadays. Okay. So we can also mix the vector registers and the scalar registers. Also, the processor may have the vector registers. And so this is some example code like y equal a multiplied by matrix x and then plus matrix y. The vector, this is vector, and then this is the scalar value. So for this operation, the vector load can be applied. So vector load, and then vector multiply, and then this vector multiply also multiplies the scalar register with the vector register, and then store the result to the vector register. So as you can see, the computer processor can use both vector registers and then scalar registers. And then load. So this is the base address of the load instruction, and load instruction is here. Then so we can apply the vector register, and then this is the add vectors. Then store vector to the memory. So this is the load store vector architecture, and then also this vector with the vector register. Then the processor can use the scalar registers. This is another example. And then vector memory system. So also as you can see here, the vector can the vector load or vector store instruction can be also implemented with the vector memory system. So actually the vector memory system is not different from some normal memory system, but there is only some vector related instructions such as vector load or vector store instruction. So but this group load or group store just execute some grouped instruction for memory accesses. For example, this vector load is accessed fills the vector register B1, and let us assume that B1 has the 64 element. So when this load instruction is executed, and then the base address is here, the base address, and then stride is here. So for this B1 0 is filled with 0R1 plus 0R1, and then V1 0R1 plus R6, and then V1 2 is filled with 0R1 plus R6 multiplied by 2. So this is some group of load instruction for these bulk load. And then mostly this bulk load is very good for the performance, because normally the data are interleaved to the multiple banks of the memory. So a bank is some separated block that operate that can execute the independent memory instructions. So if the data is interleaved across multiple banks, then these multiple banks can be executed in parallel. So this is called the memory parallelism. So actually for the most of the vector operation, request the data so like this, then the multiple banks are accessed. So the memory parallelism is automatically applied. So this is how the data is interleaved on the memory. So let's assume that the start time is the 4 cycle here. So after 4 cycle, the x0 can be read from the memory, but this memory bank 1 received the request at this cycle, and after 4 cycle, the x1 can be read from the bank 1, and next bank 2, bank 3, and then bank 4. So this is how the data request for the vector register is requested to the memory. And then also training and then parallel execution. This is not some. I don't think this is an important issue, but let's see this code. So when you this code, this is the some vector instruction. What's the problem? What is the problem? So for this load instruction, this load instruction is the instruction just equivalent to the 64 bulk load instruction. Now how about this multiply? Actually, this is the 64 multiply. So if this instruction is not pipelined, then the processor performs the 64 load and 64 multiplication and 64 load, 64 add. So it will take very long time. But as you can see, so this is a load instruction, load vector. So this load vector is applied for the 0, 1, 2, 2, 2, 2, 2 and 63, and then the mul is also applied for 0, 1, 2, 63, and then load, and then add. So as you can see, when this load instruction is fetch the data for element 0, then multiplier instruction can be executed. But if the processor wait until the load instruction fetch the all element of the vector register, then the multiply instruction will start at clock cycle 64. So it's a load, and then it's a multiply. So training means that actually when the data is ready by this load instruction, the multiply instruction can be executed here, and then load instruction can be executed here if the vector operation is performed for the element 0, and then add instruction is executed here. This is the chaining and parallelism of the vector operation. So with this training, then we can reduce the execution time of the vector operation. Normally, yeah, that is also another technique. And then scatter and gather. So what is so actually when we perform the matrix operation, the matrix operation is the sparse matrix operation. So what is the sparse matrix? Sparse matrix means that the large number of matrix element value is 0. So and then only some very small number of element has the non-zero values. That is the scatter and gather. So that is the sparse matrix. And then what's the issue of the sparse matrix? The size of the matrix is very large, but most of the data is 0. So the memory space is wasted by these 0 values. So in order to reduce the waste of memory space for the sparse matrix, then we can use some compressed form such as the CSR. So with the CSR, the CSR just stores the index of the non-zero element, and then for this indexes, the value of the non-zero element is mapped to the index of the index vector. So with this CSR format, then we can reduce the size of vectors. So, but problem of CSR format is that the many indirect memory accesses are required. So scat and gather supports this some indexed data filling for the vector register. So like this conversion, the large sparse vector is translated into the A star. A star has some non-zero element of A, and then index vector K. So in this example, there are only 10 non-zero values here. So this is a non-zero values, and then this is the index of the vector. So based on this information, the scatter and gather fills the vector register, and then also stores the vector register based on this index and element of the vector. So what's the benefit? With this format, we need to store the 1000 element multiplied by, if it's the double word, it's the 8 byte. So we need the 80k byte. But with this, we only use the 10, 20 multiplied by 8 is the size of the data is the 160 byte. So we can just save the memory space with the 0 values. But when the matrix operation is performed, then the matrix is reconstructed in the vector as the vector registers. So with this scat and gather instruction, the vector register is filled by this non-zero values and then index vectors. Also, the final values are stored to the memory based on these indexes. So this is the scat and gather. This is so we are done on the vector processors. I briefly explain about the vector processor today, and then also we learned about the Vliw today. 예, 사실 벡터 프로세서나 Vliw는 이제 그렇게 많이 쓰진 않지만, 벡터 프로세서 같은 경우는 사실은 이 GPU랑 이런 CMD 구조랑 많이 연관이 돼 있긴 해요. 뭐 그렇기 때문에 지금은 사실 많이 중요한 주제가 되어버렸습니다. 예. 예, 그래서 뭐 수고 많았고, 다음 시간에는 우리가 GPU, CMD 구조, CMD 아키텍처에 대해서 조금 이야기를 해보도록 하겠습니다. 예, 수고 많았습니다.